Hi, this is Vivek, and today we are talking about XOR space. Now, this is one of those techniques that I personally loved when I learned it the first time, and it has helped me win actually many competitions too. It is generally used in medium hard problems where a certain part of the problem needs you to use this to make sure that you understand the properties of XOR and use it in the next part of the problem, right? And if you don't know about this particular technique, I don't think you will be able to solve a problem that uses it, okay? So that's what we'll talk about today. What is XOR space and what exactly is it used for? So generally XOR space, to understand XOR space, you need to require understanding of Gaussian elimination, which we'll talk about briefly in this video, and you don't need to actually know about it. Like generally you need to know about it, and you need to have some understanding of vector space in general. But since like we all are not that maths savvy, I will just kind of explain it in a way that you don't even need to know these things, right? We will actually learn it in an enough way so that we can solve problems, right? And I think for most cases this is good enough. Later on, if you want, you can unravel all of the underlying principles that is used and why is it working and all of the things, and then you can deep dive into the maths part of it, right? Now let's take an inspiration problem and try to understand why this kind of comes into picture, right? So say you are given 5 values, right? Let's suppose there is a set which has 5 values. Now what you need to find is what are the different number of XOR values that you can get using the subsets. So let's suppose you have the 5 elements, you pick out any subset of these 5 elements and you XOR all them. I expect that you know XOR. XOR is basically bitwise exclusive OR, right? That I am expecting that you know that 1 XOR 1 is 0, 1 0 XOR this is 1, and then 0 XOR 0 is 0, and like it's commutative and everything, right? Those properties hold true. So what we need to find is we need to build subsets and check what the XOR is and how many different unique values of XOR can you, I think different, it's mostly unique values of XOR can you actually obtain using the given numbers, right? That's what is the main problem. And if you think about it, I mean, there are 5 numbers over here. You can actually try and find out 2 to the power 5 subsets. There will be 2 to the power 5 subsets, right? If there are 5 numbers. And then you can try XORing the parts that are there in the subset and then find it out. And you will find that some elements are repetitive or some values are getting repeated. And then you can discard them and maybe put them all in set and then you can find the answer. But what if the number of numbers over here is like pretty high? I mean, let's say 10 to the power 5, 6, right? How do you solve it in that case? So all subsets are unique in this case? I think no, okay? I think no. Let's try to think about, okay, what is this 3 together is gonna build us around, right? So if you have this, if you take a XOR, what you will get is maybe 1. So 1, there are only even number of ones in this row, so it will get 0, 1, 0, 1, 0. So not 0, it will be 1 and then another 1, because whichever column has even number of ones will become 0. Whichever ones has odd number of ones, it will become 1. That's how XOR works, right? And if you see just this single element, that will also be 0, 1, 0, 1, 1, 1, right? So obviously not all subsets are unique. I mean, this subset and this subset leads to the same XOR value. So we need to find out how many different subsets exist, how many different subset XOR values exist, right? Unique XOR values exist. So what is the main idea for XOR space? Basically what we do is we convert these elements into a matrix kind of a setup, right? Where we just took all these bits of the number, like originally they are numbers, right? We just have written them in binary format. We just convert them in a row-wise fashion to a matrix format, okay? Like this, okay? This is the first thing that we do in XOR space. We try to think about it like a matrix, okay? Now, what we do with this matrix is something called as Gaussian elimination. What is Gaussian elimination? If you try to understand what it does, it basically uses certain row to reduce other rows, right? You try to like kind of subtract the row that is available with the current value from other rows so that it's only one having that value in that column. But we don't need to know Gaussian elimination. I'll show you what exactly it is. This is a space. This is a bitwise space. So I will not get into details of these mathematical notations. Very simply, what we need to do is for all positions in the order. So what we'll do is we'll go through positions. Positions means columns, one by one in order. Find a row that has 1 in that position. Find a row like in this, when you go over here, for this particular position, find a row which has 1 in it, okay? And then XOR it with all other rows that has 1 in it. So you will take this whole row and XOR it into the row that contains the 1. So this contains 1, right, in this column. So you will take this row and XOR it into the whole row. So this XOR 1 XOR 1, 0, 1 XOR 1, 0, 0 XOR 1 is 1, 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0. So this is how the row transforms, right? So you took this row and you XORed it into the other row, right, which had 1. So now once you do this operation, you see that this column now has only one row having 1. That is the main property of Gaussian elimination, that you try to use one row to eliminate others, right? Now why we are able to do these things and all, that's actually the property of XOR space and this process vector spaces and all, but we don't want to get into too much of maths today. Similarly, you go to the next row and then you see which one is available. So you go to the next row, you see that this is, so this row is done. This is like available over here. You exclude this row from the next process. You see that, okay, this row has the leading 1 over here. You use this to eliminate any other thing. So you will XOR this with this row and this will become, okay, 1 XOR 1, this will become 0. 1 XOR 0, this will become 1. Okay, let me kind of erase it and write it over here because that will be helpful. Then 1 XOR 1 will become 0. 0 XOR 1 is 1, 1 XOR 1 is 0, right? This is how the row transforms. Next, you find another row that has 1 in this column. You will find this one. Like, note that these rows are now fixed. You don't use these rows again for the same thing, right? You use this column because these leading bits are 0. So if you use this to XOR with anything else, it will not disturb this side of the part, right? That is what we are doing in Gaussian elimination, that you use this one and then you reduce this other row. So 1 XOR 1 will be 0, 0 XOR 0 will be 0, 1 XOR 1 will be 0, and so on, right? Next, you go to this particular row, you see that this no column apart from these three has 1 in it. So you skip this row because you couldn't find anything new. In this row, you found this one. You use it to eliminate anything else, but there is nothing else left which has 1 in this column. In this column, there is no one which has like 1 in it, right? So over here, you see that you have kind of completed the process. This is what is called Gaussian elimination. And you ended up with a one row with zeros and changed kind of a version of the matrix, right? Okay. So this is the final version. Now, it turns out that this Gaussian elimination is not really something that cannot be done in an incremental fashion. So let's say there was this bunch of zeros, right? So zeros cannot change any other thing. So I have just removed this particular row. Let's suppose you have another row which has 1, 1, 1 zeros coming in now, right? There is a new element inserted in this set, okay? So there was a set of 5 numbers. We kind of did a process of Gaussian elimination, got to these 4 numbers. A 0 number doesn't really make any sense because it will not change the XOR value. Let's say you insert another value, right? You can incrementally build this whole thing. So let's suppose you insert this. What we will do, we will again go through that same process and just do that again. It will turn out that will not change the previous inserted elements and only the change will happen in the new element. So you come over here, you see that there was this one, you will change it with this. So you will XOR this whole row in over here. So it will become 0, 0, 1, 0, 0, 1. Okay. Then you go to this row and you see that this is a 1, but this doesn't really have 1 anymore. So you can skip this row now. This row has 1 and there is something to reduce using this row. So you come over here, you XOR it over here. So this becomes 0. This becomes 1. This remains 1 only. Right? Then you come over here and then you see that you kind of add these two ones and then you, using this, if you reduce, you will see that this becomes 0, this becomes 0. So this becomes also 0, right? Which means we can actually incrementally append a new number and it turns out it might become 0 as well, right? It might not too. Let's see one case like that as well. But the main idea is it can be done incrementally, okay? So the first understanding is it can be done incrementally. Second thing is with the previous things, we will try to reduce the new row and you will see that whether we are getting all zeros or not. If you're not getting all zeros, then it will be something significant. Why did it become all zeros? The number that we had was 1 1 1 1 0 0, I suppose, right? So we used, if you see, we used this and this. If you XOR these three things, you will get the same value actually. Okay, that's why when you XORed them into this row, they become 0. That was the main idea. Okay, let's look at few more examples like this. So let's take 2 more examples just to understand this process so that you can actually replicate it in the code as well. So over here you have the same basis that we had created. This was something that we call as basis. Okay, and then you are adding a new thing. Okay, let's try to just use this with the basis. So we'll try to reduce from the first column because this has 1 and this new one that is incoming is also has a 1. So we need to reduce this one. You need to XOR this over here. So it becomes 0 0 0 1 1 1 1 0 0 1 1 1 1 0. So this is what it becomes. Then this row comes in, but this is already 0, so you don't use it. You come over here. This has become 1, and then you see that it actually becomes all zeros, right? So again, another number kind of became all 0. And if you see, the new number that was given could actually be formed with whatever we had already, right? Let's take another example over here. Or let's say that if this, in this same example, if we would have had a 0 over here, let's say, okay, let's run the same process once more. If you just do this again, this will become 0 0 1 1. This is 0 0 0. Okay, then you come over here, this is already 0, this come over here, you use this one to reduce this, so this becomes 0, this becomes 1, this remains 0. You come again at this row, this is over here, which you can use to reduce, and then this becomes 0, this becomes 1. Okay, so finally this becomes 0 0 0 0 0 1. So it is non-zero, right? So this is something that will get added to the basis now. Okay, this is something called as getting added to the basis. Why exactly? Because see, whatever we had, they were able to control these bits properly. But then the final number that we had right now couldn't get reduced beyond this particular bit. So now this number that is added to the basis will try and control this particular bit over here. We'll see how exactly this process works beyond this. Okay, let's do it once more. You reduce this with this particular one because this is already 0. You come over here, you reduce this with this, so this becomes 0 0. This becomes 1. Okay, this remains 1. This becomes 0, right? Then you come over here, it's already there, and then you see that these are all smaller bits. So next time in this particular column, when you try to select, this row itself gets selected. So what we will do is we will write the same thing, right, with these 2 rows over here, these 3 rows over here, because they were controlling these 3 bits. But then what we'll do is we'll just reposition this so that this one over here is written like 0 0 0 0 0 0 0 1 1 0, and then the next row would be 0 0 0 0 1 1, something like this, right? Because now this bit is being controlled by this particular vector that is given, right? These bits that are given. So that is the main idea, that some might become 0, some might not become 0, and then will get added to the basis when you insert them, right? But why exactly are we doing all of these things, right? If you see very closely, when we did all of these process, every row or every vector, every row is like a vector, okay? Every vector that is there in the basis has a bit that it is trying to control. Like whenever we had a number with a 1 over here, this particular number was actually reducing this one, okay? Whenever you have a 1 over here, this number was reducing over here, right? So every number that is there in the basis tries to control one position of the bit, okay? And that's the leading bit based on when they were inserted and all, okay? That is what we use in solving the problems that we had thought about, okay? Let's try to see a code. This is a code from a blog that I will add at the end so that you can do even further reading. The blog is very well written, so I'll refer to that because since you will have to read the rest of the problems in the same style, I didn't use my snippet, I just used the blog snippet. So over here, you can see that basis of D basically tells that whichever row, this particular thing is actually a binary number, right? This is actually a number, binary number. So, which is maintained using a mask. So, which mask of the vector whose f value is I. Basically, which mask is controlling the ith bit. Okay, let's call this 0 position, 1 position, 2 position, 3 position, 4 position, 5 position. Okay, this one loop I always try to go downwards, like d minus 1, I is greater than equal to 0, I minus minus. Okay, always use this part because it is more useful in problems. If you do it the other way around, it still works, but it is not that much helpful to solve all problems. So we decrease down the thing. It's just exactly same thing. So we come over, when you are inserting a new element, this is the new mask that we have. There are a bunch of already numbers. So this number, this binary number will be stored in basis of 5. Okay. This will be stored in, this whole number as a binary number will be stored in basis of 4. This number is stored in basis of 3. Okay. This, whatever this number is nothing but 10. So basis of 3 is 10, right? Because we are dealing with bit mask, and also we can actually use the corresponding binary representation. So that's not a problem, right? Then this will be stored in basis of 1 as of now. Okay. Now when this new number comes in, what we do is we see that if we go through bits one by one, we see that if this bit is 1 or not, if this is 0, if this bit is 0 basically, then we continue, then we skip. If this bit is 1, then if you have a basis vector stored for this particular bit like 4, then if you don't have something stored, then use this as that particular basis, or else change the current number using that number. So whatever we had stored over here, we are taking this and XORing it over here. So it becomes 0, 0, 1, 1, 0, right? Next, you go to the next number 3, it's already 0, so you skip, continue. You come over here 2, you see that this bit is 1, but none of the previously stored things are in this. So the basis of 2 has not been stored yet. So save this number in basis of 2. Okay. Save this new mask, which is after reducing the previous bits, save this in basis of 2. That is what we are doing in this code. It's just a compact representation of this matrix process that we are doing right now. And we are just storing them as bit mask or masks in corresponding bits positions, whichever they are 1 at, the first number which is 1 at, right? So that's the way to represent this in code. This is the very nice style. And whenever you are inserting, you are maintaining a size of the current basis. Like if you appended this over here, then you will increment the size. If you get to a case where we talked about it, right? This all become like a 0, let's suppose, or we did this over here. All of them became a 0. So in that case, we will not add it, right? If you go back, all of them were converted to 0. So all of them will continue and you will not add it. So the size will not increase for the basis, right? The size for the basis will not increase. That's the main idea that we are using in this problem. What is the size of the basis? And that is going to be a very, very helpful metric, okay? But this is the whole idea of XOR space. You maintain bunch of vectors or bit masks that control certain bit positions, and based on that you can solve a bunch of problems, right? That's the main idea. This is the main piece of code. Now let's see how we can solve, because you will be saying, Vivek, you have shown me so many things, but what's the use of all of these things, right? Okay, let's see. Number 1 problem, number of different XORs possible, number of unique XOR values you can create, okay? It's as simple as 2 to the power size of basis. Okay. Number of different XOR values that you can create, unique XOR values that you can create is nothing but 2 to the power size of XOR basis, right? Why exactly is that? Because anything that is converted, which becomes 0, it's like you can take that and XOR it to any other thing, right? And then whatever is left over here, they all control independent bit positions. So depending upon whether you take that in the set or not, this bit will be on or not. So if you take this number in the set, the first leading bit will be 1. If you don't take it, then that bit will be off. So all the sets of containing it and not containing it will be absolutely different, okay? Then if you think about the next bit, right? Depending upon whether you have taken it or not, of course, things get shifted, right? But then let's suppose you don't take this. If you take this, all of these will contain 1. If you don't take this, all of them will contain 0, right? That's pretty much it. Every bit is being controlled by a different number. Depending upon whether to choose it or not, you can control what numbers you can create, okay? So 2 to the power size of the basis is going to be the number of different unique values that you can create. And that's actually the problem solution of the intuition problem that we took up, right? Let's see some more variations that are asked, right? What is the largest XOR value that you can create? Interesting question. What is the largest XOR value? So we have basically bunch of like vectors over here, and using this XORs of these, we need to create large values. So maybe what we'll do is like, hey, I want to of course put this as 1, right? The leading bit. So I'll put this as 1, and currently I will include this in my set. So the current XOR is this. Okay. I included this in the set because this was 1 and I wanted a 1 over here. Next, we go to the next position. It's already 1. So no need to change it using this number, right? Because if you include it in set, this will become 0. And for binary numbers, we want to be largest. You want to keep that number 1 as far as possible. Like if the earlier number is 1, even if the rest of the things are 0, you will still be far better than that number being 0 and then everything being 1. So it's 1, so don't take this basis. Since this is 0, do we have a basis for position 4? Yes, we have a basis for position 4, which is this. So XOR this in the number. So 1 0 1 0 1 1 1 0 1 1 1 1 0 1. Okay, this is the new number. Okay, next we see this number available over here. So we have used it for this particular position. Now we go forward. Okay, now we go forward, and did I like do it properly? If you use this, right? Yeah, cool. This is correct, no problem. So we have used this and this. This is also, I've used this vector, right? So this was already 0, my mistake. This was 0, so this was 0, so this became 1, right? Then you go forward and everything is 1, so you don't want to now reduce it with any other basis, right? So main idea is initially your answer is 0, all zeros, right? Go through everything, see that if it is a 0, then use that basis and XOR it with this number to get a bigger number, because this bit will flip to 1. Then based on that, you came to this number. This was already 1, so don't flip it again. If you take this and XOR it into the number, it will flip that bit because it's controlling this bit position, right? So you don't take that. This is 0. So if you can get something, get it and flip it if possible, right? That is something how you can get the largest XOR. In this case, we can make the biggest number possible, right? It might not be possible always. That's how you can find the largest number that you can form using XORs of certain given values. Very powerful tool. Maybe find the kth largest. That's another interesting thing that we can solve in this case. Very similar to the last problem, but kth finding is a difficult task in itself, and you need to understand how does kth get generated in this case. So we talked about it, right? Either you take this first element or you not. Depending upon that, if you don't take it, you will go into the branch where the first bit will be 0. Or if you take it, the first bit will be 1, right? Now, the way we find the kth element in general is detect which side should we go to first. We have to find k equal to 5. If you go on this side or this side, the property that we can use over here is you have used this first basis to decide. You will have the rest of the vectors to control certain more bit positions. So you will have 2 to the power 3 different numbers generated over here and 2 to the power 3, because the leftover basis will have these numbers, right? So these many numbers you can generate. Now you have to find 5, right? Fifth largest. So there are 8 number over here and 8 number over here. Of course, the largest number will have a 1 in this case, right? Because there are 8 numbers that have 1 at the front. So I will go in this side for sure. Okay, I will go on this side. So we need to take it. So I have taken this particular thing as of now in the set. Okay. Next, we can again decide whether we want to take that, because we have a basis for that. We can decide whether you want to make the next one 1 or 0, right? So either you can keep this 1 1 or 1 0, right? If you take this second number, you will make this 0 and then you can go forward doing whatever you want. If you take this, if you don't take this basis, this particular vector, then it will remain 1. Now I want fifth number, right? So over here, there will be 2 more bases left. So I have 4 numbers over here and I have 4 numbers over here. Now, since I want fifth number, it will be 1, 2, 3, 4, 5. So I need to go on this side, which means I need to take this. If you want to take this, then take this number 0, 1, 1, 1, 0, 1, do a XOR, and then you will get 0, sorry, not really 0, 1, 0, which we want to go into, and then currently the numbers, the XOR of the numbers that you have taken is 1, 0, 0, 0. Now you go to the next side and then you again do the same process that, hey, do I want to go into the branch of 101 or 100 because I have a basis for the third bit as well. So I want to get, so you wanted the fifth number globally. On this side, already 4 numbers have been counted and we don't want them. So we want the first number on this side. So now you're looking for the first number, and that will of course be on this side because there are 2 numbers over here, 2 numbers over here. Why? Because if you use it, after that, you will have only one basis left, basis vector left. So I'm going to just quickly shift this all around. So you have 2 numbers. I of course want to go into this. So to go into that, I should not use it. I should not use it because if I use it, I will become 0, 0. So I should not use it and it will remain the same. And then we go into the next bit, which is, hey, do I even have a choice over here? For the second bit, I don't have anything in the basis, so I don't have a choice. So from this, I will move to directly 1, 0, 1, 0, right? And then I have a choice that whether I want to go into 1, 0, 1, 0, 1 or 1, 0, 1, 0, 0. Right? Whether if I XOR this, then it will become 1, 1. If I don't XOR it, then it will be 0, 0. I want the first largest number, so it will be on this side because these are larger. And I want the first largest number, so I will XOR it. 1 number on this side, 1 number on this side. If I take it, then I will get 1, 0, 1, 0, 1, 1. Because if I XOR this number over here on this number, you will get this. So this is the 5th largest number that you can generate using this basis. Right? That's how exactly we are generating the numbers. And I hope you have understood the usages of this basis, right? Now I highly suggest you to go through this blog that is there next. Okay, this blog, it has a lot of good problems and you will understand the basis vector in much more detail. This blog has like source of all these problems where you can submit them and as well as their code too. And similar problems, and I think few more good problems are there. I think around 6 problems are there in this blog. And that will be all for this video. But I hope now you have an understanding of what this XOR basis is and how to solve these kind of problems. I got this problem once back in 2019, I remember, when I went for the TCO regional rounds at Jaipur. So this was the third problem, hardest problem. And I think I solved it the first in the competition. I ended up being at 3rd position, but this was the first problem and I knew this technique at that point in time. So if you know this, you actually get a lot of benefits in that. And I think only 4 people were able to solve it at that point in time. So that's it for this particular video. I hope you liked the value that you got out of this. If you did, do like, subscribe and share to the video, because creating these hard contents don't really get much of appreciation. And if nobody appreciates or contributes back to supporting these kind of things, what will end up happening is nobody will create these kind of contents. So do like, share, subscribe, because that helps any content creator to grow. And then I will meet you in another video where I will talk about another interesting idea. Till then,